have to move on now with the next speaker, which is Angel Gómez Nicola from University of Madrid. And
Hello, good morning.
Hi,
Can you hear me?
Yes, and we can see you also. We see
See
your slides.
my presentation now?
Yes,
That's
we
it.
see your slides and
Okay, let me check that it changes, it moves. Okay.
yeah, it's fine. So he will
Thank you.
talk about advances on the QCD phase diagram from what identities and effective theories. Please go ahead.
Okay, thank you very much, Freezeout. It's a pleasure to be here. Thanks a lot to the organizers for the nice invitation. So here's more or less what I will be talking about. Some general aspects of the QCD diagram, focusing essentially on the issue of the chiral and UA1 restoration and the interplay between those transitions. And I will try to study that problem basically from two approaches. One is based on word identities, which is more formal, based on QCD. The other one is from effective theories, where I will try to present also some additional results. If I have time, I will speak about partner susceptibilities and even chiral imbalance. Okay, so thanks to the previous talks for the nice presentations and information. Here's the main motivation of our study and possibly of everything we're doing here this morning is the QCD phase diagram. The main challenges that are still open, like the existence or nature of the critical point, or the behavior at higher densities, the BMNG scans, and so on and so forth. The main problem I will be focusing in here is in the region of zero background chemical potential, finite temperature, mostly around the nature of the chiral transition and the relation with UA1 restoration, as I said. Okay, so it's more or less well established from different groups that we have crossover transition in the physical case of 2+1 flavors, which should become a true phase transition in the massless or two massless flavors. The main observables, of course, are, as you've seen in the previous talks, are the subtract quark condensate and the scalar susceptibility, but also the existence of chiral partners and their degeneration under different symmetries is becoming more and more important, and both from the analysis of susceptibilities and screening masses. So here's some selection of results from the hot QCD group, from the subtract condensate and the scalar susceptibility, pointing out to a critical temperature about 155 MeV, which drops to 132 or so in the chiral limit with reasonable O4 scaling. Right. Same results from all the results from the Budapest-Wuppertal group, pointing out to exactly the same behavior for these quantities. Of course, this is worth mentioning the great advance that has been produced in the last few years. This has been discussed in the previous talk by the relation between the chemical freezeout curve, which can be related directly to experimental data on hydrogen yields, with the phase transition or with the phase diagram. And that has been explored under different approximations, mostly using the beam energy scan analysis of regional, but also in ALICE data. And here's just a summary of results, which is, I think, important to point out, because we're really exploring the phase diagram, at least for low chemical potential directly from experimental data. Now going more into one of the main issues I would like to discuss here, which is the nature of the transition. As is also been said here, the universality class of the transition, or even the transition order, can change depending on how strong is the breaking of the UA1 symmetry at TC. Of course, the UA1 symmetry is expected to be eventually restored, say, asymptotically. The question is whether that restoration is strong enough near the transition, especially near the chiral limit. So this is the main question around here: is the UA1 restoration effective already at TC, which is especially important to address near the chiral limit. Traditionally, the main observables or the main bilinears that have been considered in this to answer this question have to do with the isospin 1 and isospin 0 quark bilinears related, as you can see here, horizontally by an axial SU2 transformation. So that will become those will become O4 partners, whereas the vertical line indicates UA1 transformations, which will turn them into UA1 partners. Here, the lowest meson states, which are expected to saturate those bilinears, or their susceptibilities and screening masses. The pion, the I0, the light part of the sigma, the light part of the eta. Okay, so if one looks into 2+1 lattice simulations, mostly from the hot QCD group, the O4 degeneration of partners is pretty clear, although with large uncertainties in the eta delta channel, much larger than in the sigma pion channel. However, in the case of the UA1 partners, there's a significant gap of UA1 breaking at TC for physical, at least for physical masses, and as I said, for 2+1 flavors. So, however, the issue is not completely settled because for two flavor simulations, the conclusion is rather than here's the difference between pseudoscalar mesons in the isospin 1 channel, and also for the vector mesons. I'm showing it here to compare. Here, the conclusion of this analysis, as the chiral limit is approached, is not exactly the opposite, because we are in a different situation here with two flavors. But the thing is that the results are compatible with UA1 restoration at TC near the chiral limit. The physical limit, there's a small UA1 break-in, which increases with larger volumes. And as I say, the vector channel is, of course, much more efficient to show the O4 restoration than the scalar channels, or the pseudoscalar channels. Okay, so now let me discuss how the use of different theoretical approaches can shed light on this particular issue. So let me start with what identities. What identities in principle are derived formally from QCD, and they allow to connect, in particular, scalar and pseudoscalar susceptibilities among them, and also with quark condensate combinations. And that is, I will try to show you that can be useful for the discussion I was talking about. Okay, so let me focus in particular on this set of these two identities, connecting on the one hand the LS correlator, crossed correlator. This is a pseudoscalar LS susceptibility, so it's eta L eta S correlator, which through wide identities can be shown to be directly related to this chi-phi disk, which is the typical, say, parameter measuring the O4 times U1 restoration in the lattice, because it measures the difference between these two guys, pion and etal, which in a full O4 times U1 restoration should be degenerate. And it also connects, these identities connect also with the topological susceptibility, which, as you know, is the correlator of the anomaly operator. Now, the thing is that this LS correlator can be rotated into something that is zero by parity, just by transforming the eta L inside the correlator into a delta field by a proper SU2 axial transformation. So the thing is that if the O4 symmetry was exactly present in the system, so SU2 axial will be a symmetry of the system, then the degeneration of eta L and delta will lead to a vanishing of this object, this correlator, this LS cross correlator. And then through this identity, this implies also the chi-phi disk and the topological susceptibility should vanish. So in principle, this is showing that in the limit of exact, I want to point out that the word exact here, exact chiral restoration, as it would ideally happen, for instance, for two flavors in the chiral limit, one should have also UA1 restoration according to this wide identity. And this is consistent with what is seen in this lattice two flavor simulations. Now let me now talk about other channel, which is the isospin 1/2 channel. Here, the lowest energy states are the kaon and the so-called K0 star 700 or kappa. Now, this channel can also be helpful to understand this issue about the difference between the 2+1 and the two flavor results, in particular the role of strangeness. Why? Well, there's another of those wide identities, which is shown here, which connects the difference between the K and kappa susceptibilities with this combination of condensates, which is precisely the delta LS correlator used in the lattice extensively to analyze the transition. So the conclusions from this identity are several. First one is that in the exact case, again, of vanishing a light core mass and light core condensate, say in the two flavor limit, one will have exact restoration of these two guys, K and kappa, which is what is expected as is shown here, because they can be degenerated under these O4 rotations. But they are also degenerated under UA1 rotation. So the message is that this channel can also provide information about UA1 restoration. Actually, in particular, what we're saying here is that through this identity, in the physical case, with physical masses and 2+1 flavor limit, the strength of UA1 breaking is given by precisely as something that is very well determined in the lattice, which is this delta LS correlator, that this delta LS combination. And furthermore, the tail of this curve here is driven by the behavior as SS bar. So so it's the behavior of the strange condensate here. So this is a hint which may help to clarify the role of strangeness in this apparent controversy between the 2+1 and 2 flavor results. Or in other words, in that way, one can try to reconcile them. This is work in progress we're doing at the moment. Okay, now from the side of effective theories, well, in principle, effective theories are needed if you want to have a realistic description of below the transition in terms of physical hadrons. The lightest states can be accounted for by chiral perturbation theory or unitarized extensions of it, including also the eta prime if necessary through a proper 1/nc counting here. Now, the existence of unitarized interactions improves very much the description below the transition, as I will show now, because allows to generate thermal resonances, or in other words, dynamical generation of the lightest resonance states, like the sigma or the rho, including their thermal properties, including their modification of their thermal spectral properties. Of course, one can always include hadron resonant gas-like approaches to include more heavier states. But as we're going to see in a moment, there are still relevant observables with a description based only on KPT and its unitarized version can still be useful for chiral symmetry restoration. Okay, so let me show now some results on this KPT and unitarized KPT approach. Well, first of all, the issue of partners I was discussing before is confirmed by the KPT analysis. We get a UA1 restoration of about 1.1, the chiral restoration, but this is to be taken with care because these are, of course, extrapolations to a region where, in principle, this KPT approach may not work. But what is more interesting is that as one plots the different, say, pseudo-critical temperatures, so the generation of pion sigma, the generation of pion delta, the generation of pion eta, pointing to O4 and UA1 restoration, they clearly merge near the chiral limit to a single temperature. So this is again showing that this O4 times UA1 restoration in exact chiral limit for exact chiral restoration is consistent with what we said before from the wide identities analysis. Let me say also a few words about the role of the disconnected susceptibility in O4 times UA1 restoration. Well, the thing is that one can, this is a very rather technical point, but I would like to point it out here because our KPT analysis says something useful about it, I think. Well, this is a way one can relate this chi-phi disk parameter with this disconnected part of the scalar susceptibility, because these two are generally analyzed in lattice. This is an interesting connection, and apparently shows, or it can lead to a conflict with the fact that if UA1 is approximately restored, then this guy here should vanish, whereas this guy should peak, which at the chiral symmetry. This is apparent conflict. This is an apparent conflict, and I would try to convince you that this is not so if one analyzes things properly. So the thing is that first, near TC, near the chiral restoration, where pion and sigma degenerate, so this term vanishes. These two guys, the chi-phi disk and chi disconnected, actually peak with the same coefficient. When I say peak here, I put it here in the chi-pt version of it, which is just taking the chiral limit and picking up the leading infrared 1/n pi correction, which goes like T/n pi. Because this term is regular, this is actually consistent with the fact that both can peak at the transition, at the exact chiral transition. However, if the mass is vanishing but still non-zero, and one can have another temperature, which is called here TC3, which is a temperature at which chi-phi disk vanishes, because the coefficient of the divergent term here is the same for the disconnected part and for the sigma part here, which is still present. Now what vanishes is pi vanishes with eta, whereas this remains regular. So the thing is that these two red guys peak with the same coefficient implies that they actually cancel. The leading coefficient cancels, and it's consistent to have a vanishing chi-phi disconnected here with having a peaking disconnected susceptibility. I'm showing now this more quantitatively in this plot, where I plot the different susceptibilities involved here. The red one is the chi-phi disconnected. This point here is the TC3, so it's the, say, UA1 restoration. Notice the extremely small difference between these two temperatures and the extremely small mass here of the pion mass. Now, as I say, the vanishing here of this red curve is compatible with the blue one, which is the disconnected susceptibility, is still peaking or still having a sizable value, whereas both at the chiral temperature will actually peak with the same coefficient, and this is perfectly compatible. There's no problem about that. So the message here is that the chi disconnected, the disconnected susceptibility may not be the best O4 times U1 indicator near the chiral limit. Okay, now let me jump to another interesting result, which is the description of the scalar susceptibility through unitarized chi-pt. What we've been doing here is to calculate saturated susceptibility with the basically pole mass coming from the real part of this thermal sigma, thermal F0500 that I was telling you about. You calculate it from unitarized chi-pt pi scattering at finite temperature. By the way, as Maria Paola was pointing out, we expect the same scaling also for screening masses, which have been testing with QCD data using the wide identities. I will be happy to discuss this also in the discussion session. Okay, so this susceptibility, say saturated by the lattice thermal scalar pole, behaves extremely well near the transition, even being only a description based on a single thermal state. Here I'm showing some plots, some fits of this saturated susceptibility compared to some hydrogen resonant gas fit. The conclusions given here, this thermal F0 approach is much better around TC, and what is more important, it reproduces the expected peak around the critical temperature, which is of course not covered by the hydrogen resonant gas approximation, where one expects something that is monotonically increasing. So this is an important result from our unitarized chi-pt approach. Let me show also some results sorry, for the topological chart, which is also an important indicator in case one is interested about UA1 restoration. Well, we have been calculating this in U3 chi-pt, which includes the eta prime. Here's the leading order t = 0 result, which reproduces all the spectral limits of, say, the SU2, the SU3 limit. The numerical results at t = 0 are reasonably compelling with the lattice, pointing out that the eta prima loop corrections and the eta prime mixing is of the same order as the SU3, K, and eta loop corrections, but the leading order is still dominated by the SU2 contribution. And this analysis has also the advantage of offering a neat 1 over NC expansion of the topological susceptibility and the fourth order cumulant, which is compatible with results found in the lattice. Now at finite temperature, although the lattice data here have much larger uncertainties, we still have something which is reasonably well described by this simple U3-KPT approach, even far beyond what is expected to work. Dominated reasonably by the quark condensate, as this is something that was argued in some papers, that the scaling of the topological susceptibility should be the same as the quark condensate. Well, the thing is that it is for low temperature, but near the transition, precisely because the existence of this other wide identity, which has an additional term here going with the topological chiral susceptibility, this second term is important and actually is consistent with the existence of a O4 times U1 gap in physical case, because otherwise it will vanish and will in the physical case. Right. Finally, let me say some few words about recent results we've been doing with chiral imbalance. Chiral imbalance means including a mu5 chemical potential in the chiral Lagrangian, trying to accommodate the approximate conservation of the chiral charge if the characteristic LR time fluctuation is much larger than the 5-volt expansion, which is probably true for light quarks, probably not so for including the strange quarks. So what we're doing is dealing with the SU2 situation. We were more interested in this goal, constructing the most general effective Lagrangian for non-zero axial chemical potential, and we've been doing so through the so-called external source method of the of KPT, which includes different types of terms coming from covariant derivatives and for explicit source terms. And the end result is that one gets corrections to both the second order chiral Lagrangian and the fourth order chiral Lagrangian. The second order chiral Lagrangian is just a constant contribution that will change only the free energy density and the chiral charge density. Whereas to fourth order, one has these corrections where these kappa are new low energy constants, they have to be fixed. Let me show some results. The first interesting result is that the dispersion relation gets modified in this way. One has pion velocity smaller than 1 and a different screening and pole masses coming from these corrections here, which breaks Lorentz covariance, which is of course allowed here because we're introducing a chemical potential term. There are no lattice data for the suspension relation or screening masses, but there are for the quark condensate. What we get is consistent with an increasing critical temperature with chemical potential, with a few data that are available there, and the massless limit, the chiral limit, fits reasonably well this ratio here, and allows to pin down at least one of these combination of low energy constants. Here results also for where we have lattice data available for the chiral charge density and the topological susceptibility. Again, this allows to fix some of those low energy constants, but still we need more lattice data to better pin down these kappa low energy constants that I showed before. Okay, so now I just showing my conclusions. The nature of chiral transition and the interplay of the transition with the UA1 symmetry are of course key concepts to understand properly the QCD phase diagram. There's a clear consensus that is a stronger UA1 breaking for 2+1 flavors, although as I say, the rollover strangeness and the chiral limit needs still to be properly understood. I'll be happy to talk about this in the discussion session. And I've been using two approaches. One is based on wide identities, which shows that O4 times U1 is actually restored if chiral symmetry is exactly restored, which is consistent with the results found for two flavors in the lattice. And I've also pointed out that this kappa kaon channel may be also suitable to study the role of strangeness, and then which probably may help to reconcile the two descriptions in a way taking into account that the strangeness is always there, and the presence of the strangeness is possibly what is causing this discrepancy. Finally, from effective theories, I've shown you that the description of patterns and partners of U1 and O4 is consistent with the wide identity analysis, and also that the one can have a very good description of the saturated scalar susceptibility by this thermal F0500. Also, I've shown results on the topological susceptibility, the fourth order cumulant, which are well described by U3 KPT, and including non-zero mu5 chemical potential is also reasonably okay in KPT for, say, chemical potentials below 600 MeV or so, including the final temperature effects. And that's all. Thank you very much, and thanks for your attention.
Yeah, thank you, Angel, for also staying in time and the nice open questions that you bring up in discussions. We have the chance to ask a few questions now. Are there questions? Then you should raise your hand. Well, maybe then I can just ask one question. So, of course,
Sure.
an interesting issue you raise is the difference between UA1 breaking of UA1 breaking in 2 and 2+1 flavor QCD. So, is there any evidence for the different behavior aside from the lattice results, that 2+1 behaves differently from 2 flavor?
You mean theoretical evidence?
Yeah.
Well, as I said, what we see, especially in the K-on channel, in the isospin Waldhoff channel, both from wide identities and from the effective theory description, shows that probably the role of the strange Hall condensate here is, it may be an issue more relevant than what it was thought before. I mean, say this combination is taken, as you well know, for technical reasons in the lattice, but it happens to be the same combination related to this difference. And these two guides apparently will become degenerate if both O4 and UA1 symmetries are restored. So in this sense, the role of strangeness here, so which is present in the 2+1 results, may I wouldn't say explain, but I would say help to understand perhaps this residual UA1 breaking that one has in the 2+1 case, which apparently disappears in the 2 flavor limit. That's what I can say for the moment.
Yeah, but this term also drops out in the chiral limit.
But it drops on the chiral limit, but in the physical case may explain why the combination of strangeness and chiral mass will be important.
Okay, so maybe we discuss that more in the discussion section. Are there other comments or questions? Okay, if not, then we postpone the discussion to the discussion session, and thank Angel again.